You ready to go? How's it going? Any logistical questions? The two things which happened is that we announced our office hours. Mine are Thursdays right away after the lecture. So let's say 11 till 12 in my office. TAs, let me maybe show this table just to make sure that we are on the same page. So we can go somewhere. So here, for example, let's see. So office hours, mine 11, 12, Soham, Ruchia, Avia. Still not there. Sorry, I apologize. Here. This one. So that's what I wanted to show you, right? So these are our office hours. Like historically, what happens is that typically there will be some number of people who cannot go to any of those, I don't know, have classes and everything. So shoot us an email. We might do a poll and try to reshuffle. It's unlikely that I will change mine, but it's doable as well. If it's like doesn't work for most people, I'll figure out different time. Right, but please come to us because okay, cool. We'll try to help as much as we can with homeworks, right? And the second thing which happened is that we actually signed the first homework, right? So this shell, so everyone saw it, right? I always add assignments on Piazza to make sure that not on Piazza, on Canvas to make sure that you guys have it in your calendar and get an announcement, right? So, but the homework asks you to build a simple shell. So some people did it in the past. We provide like a lot of detailed instructions for how to do it, but it looks kind of long, but really it's just more of a reading. And then we ask you to set up Visual Studio Code and specifically set up the GDB remote debugging capability with Visual Studio Code. And that like again, in the past I used only GDB in this class, but then I realized that people are very reluctant using it because maybe it hits you as a truck. I don't know. But so the first assignment or the first couple of assignments we will do with Visual Studio Code kind of to warm up. And then I will maybe ask you to use GDB natively just because there will be cases in your life when you will have to use GDB, right? Question. Well, I mean, you can code in any text editor you like, but the running GDB will be in the terminal, yeah. And the reason for that is that there will be cases where actually I don't know, maybe Visual Studio, I assume that they matured enough to have everything what I like might be available from Visual Studio, but it's kind of re-exporting GDB's functionality. So using GDB or being familiar with it will help you in some corner case situations. Although, like I've seen people passing this class without touching GDB. You know, brute force is a powerful thing. Okay, so homework, right? Any questions about it? You will submit on Gradescope, and unless we already have, we'll have an auto grader which just asks you, okay, you passed those cases. You can submit as many times as you like. The goal is to pass the test cases. There are ways to cheat on the auto grader. Do not recommend it, but okay, good. So any other questions about logistics? We also had the first quiz, which I assigned over the weekend. I've seen people who said, okay, I didn't realize there's a quiz. I forgot about it. So I extended it by 1 day until yesterday's night. So I hope now everyone is okay with it, right? So, but we will have a quiz, I would say almost every week on a weekend, right? So just be ready for that. But again, I will put it on Canvas, so you will have an announcement. But if you're traveling for the weekend, I mean, if something drastic happens, just shoot me an email. We'll try to accommodate you if you suddenly miss the quiz. I try not to miss. Okay, that's it. That's what I have. So office hours, first homework. Like there was some discussion about the misconduct policy on quizzes. Like again, it's a little unusual maybe, but the policy is very liberal. You can use any resources. You can search internet during the quizzes, but the main kind of goal is that you read through those assignments, which I'm assigning every week. It's not like a ton of reading, but it's a little bit of reading. If you read this, you supposedly can answer the questions. Just they are not hard. Like quizzes will go up and down in complexity, right? But they will not be like super hard. And so that's the main goal. You read the material, you kind of follow what's going on. You watch the lectures if you miss them. You answer the questions. If you struggle, I've seen in the past that people start ChatGPT, even before ChatGPT became a big thing, right? So people said, okay, we just dump the questions and get the answers 50% correct. Maybe it improved. So sure, go ahead. If you need the help from ChatGPT, go for it. I don't recommend it because it's again very, very noisy, but maybe your masters of creating prompts and everything will fly for you. The only requirement is that I request you in the last question to disclose the use of ChatGPT or other AI tools and dump the complete history of the prompts, right? So, but again, if it helps, go for it. So I try to be realistic. I know that people will try to do that, but that's the point. But the point, and you can ask, like another thing is that, can I discuss it with my friends? Yes, you can. I mean, realistically, again, people will discuss, and I don't mind. Like discussing things is good, right? The only thing is that do not just straight copy the answers. If you're unsure in your answer, you can ask your friend and grill that friend on like, okay, why do you think so? And that friend has to explain you why. And if you agree, put the answer. If you're hesitant, but your friend is historically has better grades, you can also take the answer, but try to understand what's going on, right? So again, very, very permissive policy. And the same will be, okay, exams. I wanted to make sure that we understand it. So midterms and final, there will be open book. So you don't have to try to remember anything. You can use any class material. I usually say anything available from the class web page, which means that you can take your computer, open it, click the links, search through the lectures, search through the books, use the tools like GDB, compile code, do whatever you like. It's allowed. The only two things are not allowed, or three at this point. First is search is not allowed. So you cannot just search Google and say, look, okay, what does it mean? Why? The only reason is that the answers are so noisy that it's very hard to really say, like, get any meaning out of it. Like, really, Google is not that smart at this point. Same for ChatGPT, not allowed. And third, obviously, communication. So you're not allowed to communicate. But everything else is open book. Just make sure that, like, you don't have to remember anything. Just make sure that you understand what's going on, be able to find an answer on the exams. But on quizzes, you can use ChatGPT if you like. Just disclose it. Same for homeworks. I will add a field in a grade scope, so you can like disclose the use of ChatGPT. If you feel like that in order to build a shell, you need ChatGPT, go for it. But just again, it's up to you. That's like in your adult life or professional life, the real, you have to build some bindings to some obscure Python libraries. You have no idea how to invoke the interfaces. Back in the days, you go online and search for an example. Today you have whatever, copilots and stuff. So that's a sound use of those tools. But if you want to do something smart, try to do it yourself, because the tools will not help you that much. But okay, that's oh man. Any other questions? Enough talking. Okay, back to the lecture. So hopefully everything is clear. Everything is very super duper permissive. Everyone should be happy. Stuff like that, right? We're back to this. We're back to this lecture, and let me just make sure that I reshare. Maybe I'm sharing actually, but let's just double check. the lecture, which still talks about the calling conventions, right? So this is what we started last time, and I hope we will be able to finish. No, I will be able to finish today and start the new one. The thing here is that again, just reminding the goal. The goal is to make sure that we 100% clear about what's going on in a program. What does it mean to run something? And we are targeting specifically programs generated from C. And I'm not going to cover anything else, unfortunately, but it's not that hard to make a step forward and see, okay, I understand that Java has a thin runtime, which is C-like, which first boots and then runs the program and stuff like that. But still, it's more like running a C program. Similar for other languages. So like maybe Go or Rust, they might require a slightly different setup, but they kind of like run in the same manner. And in order to start running something, we need to understand like the prerequisites. What is that we need to run? And what is that the operating system needs to set up inside the exact system call to jump into your main function, right? Roughly speaking, it's like it has to set up the stack. It has to set up arguments, which the shell passes into main, right? Stuff like that. So, and that's what we're doing here. And we'll be doing next week as well. Okay, so we stopped around here. So we were talking about how to pass the arguments. So essentially, if I have a function, something like foo, and it takes 3 arguments, int a, int b, and int c, like where do these go? Do you remember where they go on this? I mean, first of all, we keep talking about something what is called a calling convention, which means that probably there are multiple calling conventions. There are like there is at least like a dozen of them. We will click the Wikipedia link and take a look at them. But at least if you understand one, you will know how others work as well. For this 32-bit machines, which we're discussing, 32-bit x86 Unix systems, how do we pass arguments? Who remembers? You put them in a special registers. Any other opinions? Exactly. So on 32-bit machines, the convention is, this convention is that, and there will be different ones, that you push them all on the stack. On 64-bit machines, you push a couple of them in registers just to save time of pushing something and popping on a stack. And like essentially that's the convention. So, but on this one, on 32-bit machines, and we will be covering like our x86 version will be 32-bit version just for simplicity. Like everything is pushed on a stack, right? And return values are returned in these 2 registers, EAX and EDX. And in 99.9% of the cases, you will only see EAX. As I mentioned last time, its use of EDX is so rare that I don't remember myself. I keep looking it up every year and I keep forgetting it later. So just remember this one, EAX. EAX is for returning registers, for returning values. On 64-bit machines, you know, the convention is slightly different. The first 6 arguments go into these registers in this order. First one goes into the RDI, second RSI, and so on. And if you have more than 6, then you start pushing them on a stack. But return values go into those again, RAX, RDX, which are 64-bit versions of the same registers, of the same 32-bit registers. Okay, and we were somewhere around here, so I was talking about those examples, and we'll take a look at more examples today. So if you have this function, my function, which takes 3 arguments, and you try to invoke it passing 3 values, 2, 5, and 10, the call site, or when you try to invoke this function, the compiler, so like for this kind of code, right? The compiler will generate this assembly. It will say, look, I will push the 3 arguments on a stack, and then I will use a call instruction to call my function label, right? So the 3 will be on a stack. And so when you obviously somewhere here, you should probably release this space on a stack, because the goal is by the time you reach the ret instruction, like at the very top of the stack, you will need to have a return address, right? So you have to make sure that the stack is like allocated and deallocated symmetrically, which is not super hard. And normally you don't even like, you don't bother because compilers do it for you, right? Unless you really like have something where you have to do something in assembly, then it's all hidden, but still understanding of it is required. So let's go through a couple of examples, right? So a typical layout of the stack, right, is the following. That's what we were talking about. And I just try to remind you. And like again, maybe it looks a little bit like intimidating again. This is the stack. It grows down, right? So remember, before calling the function, is in our example on a previous slide, we first push the third argument. So this is what we've done here. So we first push the last argument. So this 10 is the last argument to the function, right? So it's pushed first on a stack. Then we push the second argument, then we push the first argument. Then we invoke the call instruction. Call instruction pushes the return address on a stack. And so the return address will be here on a stack. If the code, the compiler itself, maintain the stack frame, and up until now, I just assume that stack frame is always maintained, and we'll discuss it in a second, whether it's always maintained or not, then the prologue of the function will do something like push the old value of the EBP on a stack, and that's why EBP will be saved. The previous value of EBP will be on a stack, right? Then the next instruction, like part of the prologue, it will just do something like move the current value of the ESP, sorry, it's Intel syntax, EBP, ESP. Move the current value of the stack pointer into the EBP to initialize the new stack frame, right? That's why EBP will be pointing specifically to this location, right? It's important because there will be assignments which will require you on both midterm and in homeworks will require you to like reason about what's on a stack, meaning that you dump the memory and I say that's a stack at this point, and you have to annotate each value on a stack. And roughly speaking, this is how you annotate, right? And okay, cool. And then if you, in the function, remember, if you have local variables, we've seen some optimizations when local variables don't even get allocated to the stack, they just kept in a register, in registers. But if they are, then, you know, like first local variable goes right away on a stack. And so it will be, if EBP points right here, right, then the next position on the stack, this one, can be addressed as EBP minus 4, right? And so on, EBP minus X. And the current like stack frame points exactly here. This is the, if you just do something like move into a register EAX some EBP, so you're essentially loading this value. Is it clear? Just because this is how everything is maintained. This is how the stack is maintained, and two registers, EBP and ESP, are maintained as well. Any questions about this? What's the use case for what?
The result.
For doing this? Obviously, this is extremely rare. So the use case for EBP minus, for example, 4 will be accessing the local variable, right? EBP plus 8, accessing arguments. You will, in a typical code, you will not change EBP. But if you're building something like asynchronous runtimes, which play with stacks, like in Rust, for example, you have a sync, right? I don't know, C++ also maybe have a sync at this point, where, I mean, where you build like a closure or continuation. Then you might, the runtime itself might manipulate the stack, make sure that everything is saved and restored. But typically, again, I don't want to go into too many details, but that's what happens. Any other questions? EBP stands, again, it's a wisdom of Intel, and I don't know the history enough. It's a bottom pointer. Points to the, I guess, bottom of a stack frame. But this is how it's used to maintain the stack frame. But to your right, so let me, okay, if you ask me on Piazza, I will go and try to figure out historical reference for this, but I don't know exactly. Any other questions? it's better if you guys understand this, because it will come back in many, many assignments. So let's go through more examples. Again, I assume that it's very simple, like nothing is happening here. Just we're looking at assembly code, and in a second we'll look at real assembly programs which will generate from C files, just to confirm that whatever the current tools are doing, like GCC compiler, will generate exactly this code. So here, like we're looking at this piece of code. So there's a function caller, which calls a function callee. In fact, we don't even know what callee is doing, so we just have the signature of that function. This signature is sufficient to generate the call side, right? So without knowing the signature of a function, we don't know how many arguments to put, right, and everything. But what the compiler is doing, it says, okay, look, we'll maintain, save our own stack frame, so maintain it correctly. Then we use 3 push instructions to push those arguments, 1, 2, and 3 on the stack. Then we use the call instruction to call the subroutine callee. Callee returns, since we assign +5 to the return value. We first deallocate the space which we allocated here for those variables on a stack, simply subtracting 12 from the ESP pointer, stack pointer, and just do the addition of 5 to the EAX register. And the way addition works is that it takes EAX, adds 5, and save the result in EAX. So result is inside the EAX. We restore the old stack frame, it's kind of symmetrical to what we did here. We return, and I was asking a question, what about the return value? Like, where is this line? And the answer was that since we already keep the return value, this ret, inside the EAX register, we don't have to do anything. We just return, and whoever called us will get it from EAX, right? So this is clear, I hope, right? And this is probably where we approximately here we stopped last time. So here's another example, just to if we go inside the callee, and we did it multiple times, so inside the function, like any function. So just wanted to illustrate those things here. We again maintain the stack frame. If you maintain the stack frame, these 2 instructions are always executed. So for example, if I ask you a question, imagine on x86 you have a WC, word count program, and I'll ask you what is the first instruction which executes inside this program? So what will be the answer? Inside the main function of the WC program, which counts the number of words in the input. Push EBP, correct, right? So, and the logic here is that, okay, we don't know what's going on inside WC, but we know that x86 maintains the stack frame, and so the very first instruction will be this one, right? In fact, in every program which x86 starts, maybe besides modulo the very first one, which is written in assembly, which does not maintain the stack frame, this push EBP will be the instruction which executes, right? Why is this knowledge useful? You say, look, okay, you found like a really, really useful piece of knowledge. But imagine you are a security researcher and you're thinking about vulnerabilities somewhere on the other part of the world, and you somehow know, it's okay, I know that the code will, or most likely will, maintain this stack frame. And with a very high probability, you will guess that this is the first instruction which will be executing. And similar, like if you can guess what's coming, then you can leverage this to mount an attack. I'm not saying that realistically it's a very practical piece of knowledge, but still, that's the way to think about those systems. If you know general principles of how they work, you can also guess with high probability what will actually happen. Okay, cool. So EBP, maintaining the frame. So here we subtract 12 bytes because we have 3 local variables here, A, B, and C. They are all integers. On 32-bit machines, integers are 4 bytes. And so that's why 12, right? And as we like previously just discussed, so if I ask you a question like, how do you access X, for example, by looking at this slide, let me erase everything on it. You second, okay, inside the function, this is my stack layout, X is the first argument. So first argument is accessed EBP plus 8. And so this is how I will be able to find it inside the function. So this is what it says, EBP plus 8, right? So this, I just wanted to make sure that we all understand what these numbers mean, right? Agree? You just like keep going over and over, but I just believe that, I mean, how many people seen this stuff before in any of the classes or in their kind of, not bad, actually, quite, so where, which class? 4400 covers it, okay, cool.
My 4400 doesn't cover.
Didn't cover this.
We only cover steps.
Okay, good. I mean, good job on doing 4400. So x86 also has a specific instruction leave, which is equivalent of doing this too. Again, if it's not very important, but if you ever seen leave, well, if you ever see leave, then this is what it means. Okay. We talked a lot about stack frames. At this point, everyone probably is sick of our question. No, pop is just a regular instruction. It just takes the value from the top of the stack where the ESP is pointing and saves it in the register, right? And decrements the stack pointer, increments the stack pointer by 4 because it releases space on the stack, right? Do you agree? No, it's important to understand like push and pop. Push, like this one, saves this value. So imagine you have ESP here pointing to some 4 bytes on a stack. If I remember correctly, ESP gets incremented by 4. So it doesn't override this value. It saves the value which was inside EBP, let's say 55, saves this 55 here, and ESP now is decremented by 4, so points to this line. And pop is the reverse. So it essentially takes whatever the value was here on the stack. So if you pop inside in any register, it will take this value, put it in the register, and will increment it by the size of this. Okay, this is, first of all, I think this is a great question. So you're asking what happens to the local variables, right? What do you think happens? They get what? Overwritten eventually. But okay, so push and pop instructions do not erase those values on a stack, right? They leave them there with the hope that the space will be reused later. But for example, there might be a range of bugs or attacks in your code. For example, if you use an uninitialized variable like X, and instead of like setting it to 0, the compiler just allocates space for this. And maybe it just gets allocated over like any value, like maybe 55. And then it has some value which like leads to some random corruption. That's okay. The program crosses, not ideal, but more sophisticated attacks allow you to leak sensitive data. So for example, you had the data structure which had a part of your password, right? So letters of the password, which were allocated on a stack. If you don't clean the stack, and then later somehow call a function which allocates an uninitialized variable and somehow leak this variable outside, you can leak a password. And those are real attacks. I can point you to real CVEs in the Linux kernel, which use those things to leak information from the kernel. And it gets even more sophisticated. So it gets sophisticated. Sometimes okay, I don't want to go into it, but sometimes when you have a data structure, the rules of the language sometimes they always request natural alignment of those fields to their natural lengths. So for example, if this is a 4-byte field, it will be 4-byte aligned. And so meaning that you have these 3 fields, but this little gap in the data structure is just padding. And in many cases, the compilers generate the code which leave this padding uninitialized, despite the fact that other fields are like overwritten with zeros. So there will be assignments to those fields, but this padding may get leaked. So there's like, it gets tweaked. But okay, what's important here is that you're right. So the values on the stack remain. And so if you're very careful and clever, you can make use of those old values. And in our class, what will happen or occasionally happens when you start building when you work on homeworks and you say, look, I believe I'm inside function foo, because look, the stack is pointing to this and this, and I'm clearly, my code has to land me on the function foo. But in practice, something like, you overwrote a pointer, you jumped instead of foo to bar, you look at the stack, you see some weird values. And sometimes those values confuse you. Sometimes you say, look, sometimes you can uncover the fact that you are not inside the foo, but inside the bar, because you see something what is specific to bar. But sometimes they only confuse you. But you'll see. I mean, I don't know how really often you will see it in your life. I've seen it in mine, and it was fun, like sometimes to understand what's going on. Yeah. Because sometimes you absolutely randomly land on some part of the program and you don't even know where. Okay, any other questions? It's a good question. Okay, we're good. So, okay, I wanted to talk about this. Stack frames. I was pushing for stack frames. As you say, hopefully 4400 was pushing for them. And now came the moment of truth, like, why do we really need them? So who can tell me? Everything what I said in the lectures was very, very, seems practical. One way to go about it. Debugging. Huh? Debugging. Yeah, right. So that's good that you can guess. So in fact, there is no real reason to maintain the stack frames, because what's going on is the following. In fact, the compiler has a flag, which that flag a mid-frame pointer. And it says that don't keep the frame pointer in a register for functions that don't need that one. This avoids the instructions to save, set up, and restore frame pointers. So all these prolog and epilogue instructions disappear. It also makes an extra register available in many functions, meaning that EBP now can be used as EAX, EDX. So like there is no special meaning for EBP. And this is the comment from the GDB page. It also makes debugging impossible on some machines. So what does it mean? It means the following. So in reality, as I was maybe mentioning last time, imagine this is your stack. And imagine you pass some argument in a function, right? So it's right above the return address. Stack grows this way. Initially, this parameter is like accessible, can be accessed as ESP plus 4, because ESP points here, so ESP plus 4 is the argument, right? As you go into the function, maybe you execute some loops, you push something on a stack, pop something from a stack, do it 10 times, and somewhere later in the function, you say, look, my ESP is currently pointing here. So in order to access the same argument, the same value, instead of ESP plus 4, you suddenly have to use ESP plus 8. Well, is it bad or not? That depends, right? So it's for you as a human, it's a little hard to track, because you really will have to mentally kind of simulate execution of a program, and keep track of what got pushed on the stack, where the original values are, and check whether the code is correct, right? Or maybe if you write something in assembly, you have to write correct assembly. For a compiler, it's not a problem. Like it's easy to write an algorithm which keeps track of where stuff is on the stack, right? So, which means that, like really, it's only for the human. And for the human, really, it's only needed for debugging purposes, because sometimes you crash in a program and you say, look, what was the function which called my function? How can we answer this question? Correct. And how do we access the return address? Oh, no, man. Like, remember? No. Where is the return address? Correct. It's right above. So that's why I was like showing you this thing, right? So if you crushing inside the function foo, like segfold, accessed memory, which wasn't mapped, or do a division by zero instruction, you get a like exception. We will cover exceptions. But you really, maybe foo got called from like 10 different spots and you think, okay, what was my execution? The way to unroll this in execution or create a backtrace is that you say, look, I will look at the return address. And obviously, whoever called foo, whatever bar is, this return address, this A, will be saved here, right, on the stack. And so you can see where, like, I'll talk about it in next week. You see where this A falls. A falls inside bar. It means that bar called you, right? And how do you access this return address? You simply say EBP plus 4, right? And okay, sure, but how do we know the function which called bar? This one. What do we do next? Correct, because as you say, your old stack frame is saved here, which points somewhere here on a stack, which will have its own EBP. And right above it, there will be return address here, right? And so you say, look, okay, whatever is saved here, which is B, for example, that called me because it's a return address from here, right? And so you can walk the stack up to the very first frame. EBP will probably set to 0 or to some constant. Typically, it will be inside, like called by the operating system, and you can at least have the stack frame, right? Or the call trace. Agree with this? Does it make sense? It will come back in the homework assignment. Don't worry. But like you will have to reason about it. But at least the high level logic of how to do it is clear, right? And that's nice. And we will use it inside x86. And okay, compilers, they can generate enough debug information to provide you as a human with this information without EBP. But if we don't maintain the stack frame for you as a human, it becomes a little harder, or hard. That's why in our class, we argue to maintain the stack frame, and x86 will maintain the stack frame so you can do this exercise and do the backtrace and see what's happening in the code. Make sense? So what are the advantages or disadvantages of maintaining the stack frame? Like we got it. Advantages is essentially we get back debugging. So as I was saying, compiler can generate this information for us because it's smart, but it's hard for us as humans. What will be the advantages of not maintaining the stack frame? Anyone? Correct. You're wasting instructions. Okay, can you be more specific? Correct. So essentially, these two instructions and this one, roughly 3 instructions, are wasted. If I ask you a question, what do you think in terms of cycles? How much cycles? How many cycles you waste? Again, trying to prepare the next generation of top-of-the-line coders. Maybe like 5. Okay, give us, how do you count? So push, how many cycles the push takes? No, you're right. So L1 cache. And I argue that on modern machines, L1 cache, access to L1 cache takes 2 to 3 cycles, right? Question? Or what about this move? Okay, great question. So I was waiting for it and I was hesitating whether I should go into this right away, because sometimes people complain that I go into too many unrelated details, right? Okay. So how can we make this argument? I will ask you guys. So I said that push EBP touches the L1 cache. So push saves something, or the value of the EBP in this concrete example, to the memory location pointed by the ESP register, right? So what's the logic here? Why is it in the L1 cache? Like, do we know caches, caching hierarchy of the CPU in general? Or do we need a refresher? Question? No. So like, let me, I mean, it's all very useful, despite the fact that it kind of like moves us away from the main line of the lecture, but today we have time. So CPUs, just reminder, very quick reminder, we'll come back to this in the class, so don't worry. Use a caching hierarchy. So CPUs have like 8 registers, as we said. And every move instruction, like imagine you loading something inside the EAX register from EBP, or I don't know why I said EBP, EBX register, right? From memory into EAX. So typically you would say, look, memory is sitting here, like below the CPU. So if you have a CPU boundary, the memory controller is still on the CPU, but the bus takes you below the CPU package, right? So this is your DIMM, right? If you just blindly allow every move instruction to go and touch memory, that will take you quite a bit of cycles, because this link to memory is roughly 250 cycles on modern machines, and I will provide you later a link to literature which measures those cycles, right? So if you say, okay, every instruction which goes to memory touches memory, then you're stuck. So because your CPU doesn't do anything for 250 cycles, right? So CPUs introduce this caching hierarchy, and typically on modern machines, it's 3 levels of caching, L1, L2, and L3. And when you first read the cache line, it will be placed, depending on the policy, in either all levels of this hierarchy and retain there for some time, with the goal that if you read it again, it will, you will access it faster, because instead of going to memory, you either find it inside L1, which takes roughly 2 to 3 cycles, or maybe if it's evicted from there, inside L2, which takes roughly 12 cycles, or maybe inside L3, which roughly takes, let's say, 40 cycles. I bold the number here, right? And obviously, any instruction which touches memory, like a move instruction or a push instruction, EBP or whatever, ESP or anything, push anything, will touch the memory. But probabilistically, right, since you were calling and returning from those functions recently, most likely the cache line which you're accessing will be cached somewhere in a caching hierarchy. I mean, of course, when you call the very first function for the very first time, like when you call main, it will not be cached. It's the very first access to the stack. Then you pay the price of 250 cycles, go to memory, but then it gets cached in a caching hierarchy. And so the second, third, fourth access, and you have to be specific about how this protocol works, will get amortized. And probabilistically, there is a high probability that a push instruction which will find the cache line in a first level cache. Does it make sense? It's nice to think about it. Okay, so back to those cycles. So just to make sure that we know what are we saving, right? So we said, okay, cool. So where is it? So we were counting. This first instruction is 2 to 3 cycles. This move instruction is how many cycles? Touches 2 registers. So execute. How long does it take to execute it? 1 cycle. Agree with this? And this pop? No. Again, 2 to 3 cycles. So we're saving a total of 5 to 7 cycles, right? If I counted correctly. It's still a lot, because if you're executing a ton of functions, like really a lot of functions, it takes you time. And the entire invocation, if you also add a call instruction, which pushes something on a stack, is probably also taking 2 to 3 cycles, right? So like if you can do the invocation and return probably will read something 2 to 3 cycles. So it's another like 4 to 6 cycles added to this number. So that's the cost of a function invocation in a regular programming language. It's nice to be able to reason about those numbers. So by getting rid of the stack frame, you essentially accelerate your function invocations, and that it can make some code quite a bit faster, right? Similar, this is essentially the same logic applies for function inlining. So you've seen inlining, you see that programming languages try to inline small functions to avoid the function invocation. That's the reason for that as well. So essentially to save those cycles. And also, you get one register back. So which means that on 32-bit machines, out of your 8 registers, instead of like having 6 available because ESP and EBP were taken by function invocations and stack frame, you now will have 7 registers. So you have 1 extra register, which is kind of a huge deal because percentage-wise, it's like it's huge out of 8. On 64-bit machines, the equation slightly changes slightly because you have 16 general registers. And so maybe getting 1 extra register doesn't really matter, but still it kind of like, I would argue, it takes less than 1% of your performance, but like if you run like stack benchmarks, but it still takes some. So, but majority of the performance overhead is pushing and restoring registers. And by extension, remember the calling convention on x86 says, okay, the first 6 arguments will stay in registers. So you don't have to save them on a stack. So you're trying to prevent those push instructions, which push the arguments on the stack as well to save time for function invocations, right? So that's kind of the logic. Okay. And the way to go about it is essentially like you click this link. Can I even click it? I don't know. Let me just quickly. I just wanted to make sure that you understand that everything what I said makes sense. I'm sure. So that's essentially the GCC optimization page, and you go for frame pointer, and this is the flag, essentially which essentially just repeats what I said in this lecture. And the most important part here is that don't get surprised. In recent versions of GCC, as of like 4 years or 5 years ago, the flag is essentially on by default, meaning that if you don't specify, do not do this, the GCC will generate the code which will not generate the stack frames, right? So it's on with optimization level 1 and higher. So O0, it will still be disabled, O1, it will be on, right? That's important to understand that we know what GCC is doing as well. Okay, and just to wake up everyone and check for attendance. Let me real quick start the poll. Use this. So you probably should see, I don't show it on the screen, although maybe I should. So the question asks you in which register do we use to pass the return value, and I will try to present. How do I present this activity? Okay, like this. No, I have to do this. Everyone remembers the register? Let me show you the answers here. So this is our answers on the screen. So some people still believe this is ECX. Some believe this is EBX. Majority believe that this is EAX. Okay, hopefully we're clear on that. The reason is just, okay, in the beginning of the class, people were unsure. Hopefully now everyone is sure. So let's go to the next question. This one is active, I hope, right? In the calling convention we just discussed here in the class, which is 32 bits on Unix machines, how do we pass the first argument in the function? There is a way to present, okay, like this. So let's answer this one. Everyone knows that it's no longer EAX register. No, not everyone, but most people. Good, everyone answered? Anyone needs more time? Not working on Canvas? Man, but how do people answer then? Not working on Canvas, but works through the QR code, right? That's cute. What can I say? Okay, let's do. I didn't know that. So maybe I should really go and like do something on Canvas. Let me try. I don't know. Does it still doesn't work for you? Meaning this link or this QR code, like this one. Well, sorry. Like I'll give you points if you. Yeah, so just send me an email. Hey, like thank you for. I mean, I didn't realize that obviously, because the way the interface is designed, it kind of suggests that it should work anyway. But yeah, so then QR code, please, and then or just I assume correctly this link, right? Okay, so I will then make sure that this link is available on Canvas as well, making sure that anytime you're in class, you can say, look, cool, I'll go to the home and do this. And I will put it on the class webpage as well. Okay, but shoot me an email. So this one, okay. Okay, hopefully, again, everyone answered. All good? Everyone knows that it's on a stack. That's good. Okay, so then I will deactivate this one, go back to the lecture real quick. So, and try to finish. So last bits of our calling convention is the idea that we need to save and restore registers, or need a convention about saving and restoring registers. Can someone tell me why? What is this convention about? Why do we need such a convention? Anyone? Correct, in a way, right? So yeah, so when you do call a function foo, imagine you had some value here in the register EAX. You need a convention to agree whether foo will preserve the same value of EAX after the invocation, right? Because, well, maybe if you say, look, foo has to preserve all the registers, then really the first instructions inside foo should be push EAX, push EBX, and so on. Every register which foo uses should be pushed on the stack, right? And then restore. And obviously, this is not the case because EAX is used for return value. So clearly this register will go away, right? So if you had something in EAX here after calling the foo, register EAX will be overwritten with the return value, unless it's a void function, right? And so this convention is needed. And like design choices here is to make sure that it's practical enough so you don't have to save every register, and sub-registers can be like leave untouched. And so the convention is like that. First of all, we have to understand that when you do a call function, it's kind of clear from everything what I said, the processor doesn't do anything. It doesn't save any registers. You know, whatever was in the register stays in the registers, right? If you use something, if you override them, the values disappear. And so essentially, they said, okay, on this architecture, registers EAX, ECX, and EDX are caller saved, meaning that if you call a function foo, those three registers after the function are undefined. Like EAX obviously is defined to contain the return value. EDX occasionally contains return value, but in general, like it's also like can be used by the function foo in any way the function wants. And so essentially those values will be gone. And so those are called caller saved. So if you want to use them before calling the function, you push EAX, push ECX, push EDX, and then here you restore them with a pop instruction, essentially saying I'll temporarily save them on a stack. That's what's done, but you can save anywhere, and then you restore them, right? And the rest of the registers are call is saved. So meaning that inside the function foo, if you are about to use the EBP pointer as then you have to save it and restore. And we saw it. So this is what the code is doing when the code maintains the stack frame pointer. But even if you don't maintain the stack pointer, the convention is the same. So if you use any of those registers, you have to save them and restore them. Make sense? And that more or less is the last important bit of those conventions. So, and again, I said, okay, we're going to go to the Wikipedia page and quickly take a look at other conventions. So if you click on this one, open a page, go to Wikipedia, like there is a page which is dedicated to all these conventions, which essentially describes like my examples are taken, some of them are taken from Wikipedia. So you quickly can, anytime you do some kind of a debugging, you see, okay, I don't know where the return value is going. You say, look, I'm going to go here. There is a table here which lists all these conventions, and ours is like different architectures, like 86 machines, like 16-bit machines, 32-bit machines, but Microsoft has a different convention, which is cdecl. We are using, which one? We are using System 5, which is this one. So cdecl Unix-like, and it will say that what I wanted to see something like I wanted to so this is a 64-bit version of this convention, and we are using a 32-bit version of this convention. But okay, these are the ones. And so you essentially what I meant to say, it will have the same bits of information which I covered. So the first 6 integer or pointer arguments are passed in registers, and those are the registers. For the extended registers, those are multimedia vectorized registers, it also has a convention, and so on and so on. Integer return values up to 64 bits are stored in the RX, while values of up to 128 bits are stored in this register pair. So I keep saying that I keep forgetting where RDX is used, but apparently on 64-bit machines you can return a 128-bit value, and the second part of this value will go into the RDX register. And if you read more carefully, you will essentially everything what I covered in class will be on this Wikipedia page, and it can be very helpful. And finally, what I wanted to finish with is this slide. So I was saying that there are 2 assembly language syntaxes, the most popular ones. One is called Intel, and this is what I was trying to cover in this class all this time. And it's essentially saying, okay, the order of the operands is from EBX to EAX. Unfortunately, there is an alternative syntax, which is called GNU or GCC or AT&T syntax. And these two things are flipped. So they have slightly different name, which probably almost ignorable. But the most important thing is that the direction of the operation is in the other direction, right? So it's reversed. It's a little confusing. Like the reason I choose Intel is that I believe that reading something like this is harder than reading something like this. And especially when they're like not just one, but like a couple of registers after comma here, then it becomes like, okay, what's going on? Like in practice, they are equivalent, right? And it's not super hard. I like Intel a little bit. I believe that Intel is a little bit more readable for a human, but essentially it's all the same. So if this is the read from a memory, which is at the address of ESI -4, so this is the same read from a memory. These brackets are slightly different and into the register EAX. Unfortunately, or fortunately, X with 6 uses the GNU syntax. So just be prepared that you will see it later in the class. In most cases, it's not very confusing, but it's still there. Okay, good. Any questions? And I will switch to I wanted to show you a couple of examples today. All good? Okay. So, okay, and finally, like what I wanted to say, like after like this 2 last lectures, I wanted to convince you, and it will take me some time, but it will take me, like we'll get there. Really? Memphis. What's the other machine? Thomas. I left my cell there. What? This one. So it's like the entire website, which we're using for the lectures, is available as a GitHub repo. So it's a public repo. You can clone it. You can take any like sources for any lectures. It uses whatever the Hugo scheme. So like it's in this static subfolder. But if I do this C command, which will take me forever, because probably I have a fair amount of files. So cancel. You can go in any of these lectures, and like we go into this one, which is calling conventions, lecture 04, calling conventions. There I will have something like source folder, src with examples. And this is where we we'll be looking at some examples. So it has a README file here, which tells you what you can do. And essentially what's going on here is that I say, okay, look, there's this main program. Let's take a look at it. What it does, it's again, very simple example. So it says, okay, I have 3 local variables, X, Y, and Z. I call the bar function, passing X, Y, X, Z as an example, get X back, assign 5 to it, increment by 5 and return, right? And the bar function takes these 3 arguments, add them together, adds 6 and returns, right? Returns X. And the reason I'm showing these examples is to make sure that we understand that everything what we covered in class is really what the modern tools essentially do. So if you do cat readme here, I say, look, if you just want to build this with GCC, so I'll build this with the GCC compiler. I'm on a 64-bit machine, but please build me a 32-bit code here. I don't want to get a position-independent code, which we'll discuss later. So I say no pick. Passing pick stands for position-independent code. Let's say let's use the debug information, and I say just compile the program main.c. Do not link it. Do not get it ready for execution. What it gives me is that it fits on one screen. So when we will do it, so it compiles, it produces this file main.o. It's an L file. You can say we'll come back to it in a second, but it's an L file. And then I suggest use this tool, which is called an objdump. And I will say, look, since we want to see it in Intel assembly, I will pass this m-m flag. And if you don't remember those flags, let me just, you say, look, I totally forgot what these flags are. You just say objdump and it will print you all the flags, right? So if it disappears on the screen, you can page it into something like a pager, like glass. Sorry, like I use the pipe command here, right? Which we covered. And then it's a pager. And so, man, what is my pager doing? Let's page into more. What is going on? Really, I failed to page. In theory, I should be able to page, but somehow I failed it. Oh, not sure. We'll figure it out later. But so anyway, the idea here is that like I want to see a disassembly of this program, and I also -R stands for show me the relocation symbols. I will explain what these are next week. But that's what we generate, right? And the reason I said, okay, I will be very careful about what I build, that I want to fit it on one screen. So literally it does fit on one screen. And it says, okay, it's a disassembly of the text section. Text is a name for the actual code section. And so, okay, this is the main function. And as we discussed in the class, so it does maintain the stack frame. So pushes the EBP, initializes EBP with the new value of the ESP, allocates space for 3 local variables. Let me just quickly go here into a different screen here. Yeah. So this is the code source of main. So it has 3 local variables, X, Y, and Z. Surprisingly, however, it doesn't use this number. If you don't know what this number is, do you know this number? I mean, to Python, it's 16, right? So I use Python as a calculator real quick to convert like text values into decimals. So why are we using 16 instead of like 12? Because the expectation was that we're going to be using 12, right? Because we said, look, you have 3 local variables. All optimizations are disabled. We're running at 0, right? So 3 by 4 should be 12. But here it subtracts 16 from the stack pointer. Anyone knows? Correct. So it's done for alignment. The reasons for this specific alignment are a little bit more complicated than just performance. I think some instructions, some MMX instructions, which are like vectorized instructions, operate only on 16-byte aligned values. And so if those values are on the stack and they are not aligned, you will get an exception. That's my reading, although I mean, really, this is the part where like it gets kind of hazy and you don't really know the real answer, but it's alignment. And so if you see something like this, the stack will be maintained in 16-byte alignments, right? Although like you have to go online and try to figure out what's going on. Then later on, we initialize the values X, Y, and Z with 1, 2, and 3. And this is exactly what this code is doing. So it says, okay, I will be using EBP minus these values, -4, -8, -12 to initialize them, right? So literally writing those constant on the stack. Then you say, look, I'm about to call a function. So I will pass these 3 arguments, X, Y, and Z. So I will push them on the stack exactly as the calling convention requires. Then I invoke a function. And if you're very, very careful, you will understand that it's like a negative number. And we will talk about it, but it's like the symbol which needs to be relocated, but it leads us to bar. Then we are inside the bar function here. Again, pushing EBP on a stack, initializing EBP with the new value. Again, allocating 16 bytes on a stack to make sure that we have space for this 3 local, for 1 local variable, still 16-byte alignment. Then saving from the stack into the local registers, EDX, EAX, passed arguments, doing the first addition, saving something like a 3rd argument in the AIX, doing the 2nd addition, so essentially to implement this instruction, which does A plus B plus C. And then moving AIX. That's where it gets like really like absurd, because it says, look, I have a result inside the AIX, but I'm still gonna save it in the X variable. So this assignment is really this instruction. And the reason is it does it, it's just because optimization level is O0, but we'll see what it does in O1. So essentially saving it back into memory, then like adding to this memory location, adding 6, because this is what we asked to do here. So we increment it by 6. Then, okay, following the calling convention to say, look, I know that I have to return the value in the EAX register. So please, from the stack where the local variable is allocated into the EAX register, and then this leave instruction return. Then after that, we end here and up here, right after the bar, after we invoke bar, we adding 5 to the result. We deallocate space, which we used here for pushing those arguments. We saving AX into memory where this variable is allocated, X, which is again absurd, but fine, let's do it. Adding 5 to it, moving it back into the EAX to make sure that we follow the calling convention, and then restoring the stack frame and returning. Okay, that looks dumb. That may be like the 101 compiler class, but obviously no one will ever generate this code, right? But at least it follows our understanding. So if we change the flags a little and we say something like -01, for example. Let's take a look again. Oh, damn, compilers are so smart. All the functions are gone. So it just simply knows the answer right away. So it optimized everything so badly that we don't even know, like we don't even have to invoke anything, right? It generates the bar function, which just returns 6, and generates the main function, which just returns 11 or whatever. It's 17, right? Well, don't be surprised. These are 2 extreme cases. So typically, functions do not disappear. Typically, they have bodies. You will see in your real debugging life, you will see that sometimes variables disappear aggressively. You know, it says optimized out, functions are inlined, link time optimizations are kicked in, and sometimes functions inlined later on. So it happens, but more or less, you know, in many cases, they don't. And we probably can prevent. So if we just say, oh, maybe it will not disappear. I don't know for sure. No, it still disappears. So we can probably trick the compiler to do something like maybe say volatile here. There was volatile already. Oh no, what is this? Oh man, cannot code anymore, which is absurd. Let's see if this one prevents it from optimizing everything. Or what is it I'm seeing? I deleted everything. I have issues with my wonderful term. Yeah, man. That sucks. So I ruined this example, but this one is gone. So, but let's take, we still have a couple of minutes. Is that in my full example? Something like this. So like a function which calls itself recursively. So it's a little bit more dynamic. You don't know, although here you know upfront what is that you're calling. So we can do something like again, foo.c and read the full object file. And if we even do -1, it does optimize a little, but probably will keep the function body still intact. So, but again, so, oh, by the way, so remember, O1, maintaining the stack frame disappeared. So we no longer maintain the stack frame. So no nonsense about saving and restoring KBP. So here we're allocating space for local variables, like implement a loop, stuff like that. So all these examples will be online, so you can take a look. Again, like pushing the argument, pushing 4. So this is the 4 which we push here on the stack, calling the function. But like essentially, the code actually does what you expect it to do. most interesting probably here is this loop, right? Not the loop, but essentially this if then else instruction. So again, as I was explaining, we use conditional jumps to implement those. Again, the readout here is that everything what we covered makes sense on modern machines. So this is exactly how they do it. And those examples, which I will link from the web page with all these readmes and everything, I encourage you to compile it. I don't think it's a CADE machine, but it's one of the shell machines for computer science. But essentially, this should work on any kind of like Linux, like Intel machine. On Mac, you will have to cross-compile or just deal with a different assembly, but it can also work. Okay, so let me stop here. So one announcement, however. I will be gone on Tuesday. And so Soham will teach a class, and he's kind of great. He's a PhD student, but he was in this class. He knows everything how the class progresses. He took it a couple of years ago. Now he's a TA. I unfortunately have to attend a meeting. It has to be in person, out of state. So I will fly out. We'll be back on Thursday, but come back and listen to Soham, because he's remember that in that homework assignment, which the shell assignment, he's the one who did the instructions for Visual Studio, not me. So that's his knowledge. And so it's like just to help you to learn something more practical, not just GDB, but Visual Studio Code. So I think the lecture should be good. So just please show up, and then I will continue. It will be a lecture on linking and loading, so which will take us like the entire week next week.